Today we are going to talk about Eigen Faces. It's an interesting algorithm. So there's a paper for that, which is right here, right now. So let me explain what the Eigen Faces are. So let's try to search. So by using example, it will be easier to understand. So basically, Eigen Faces, what it does is try to use PCA, which is Principal Component Access, to generate some kind of a representation of face, and then suppose if our original image is 100 by 100 pixel, so the number of pixels used to show that image is 100 by 100, which is 10,000 pixels. Now that's a lot of pixel. The thing with PCA is it tried to reduce the dimensionality from 100,000 to whatever n component we want to achieve without losing much of the information. It tried to retain as much variance as possible. That's the original purpose of PCA. But so we can use that feature to generate a representation of faces which are like this. So if you say this face can be represented using an eigenface. So now the way it does is uh, we have a higher dimensionality image reduced into multiple eigenfaces. And suppose PCA, using PCA, we have 100 components. It means we have 100 eigenfaces. So the original face can be represented as the weighted sum of all those eigenfaces. And then when you merge the weighted sum, we get our original face back. It's going to be clearer when I'm going to show the code base. So let's see. So first, what we are going to do is we are going to download some of the images. Now, there's a data set for that, which is present here. So what we are going to do is we are going to chronologically download it. So I've already downloaded the data set into my Google Drive. So and extracted data set. So this is some commands for that. You can just copy and paste, or I'll paste the link in the description. You can just look into the notebook and get the data from there. So once we have downloaded data set, our aim is to read the data. So now it's a recursive iteration of the file system to find out how many images actually we have. And turns out there is 13,233 images present there. Now we can use all the samples for our PC generation, but we are not going to go with that. So what you're going to do is we are going to import some of the samples, like we can import 1,000, 100. In our case, we are importing 500,000. So now I've already done that because this step takes too much time. So what we are trying to do is we are trying to read each and every image into its grayscale format. Like here, we just iterated over 5,000 images and read into X array. And in the Y array, we got all the names of those images. So based on the directory name, it will be clear which image is what. Like here, you can see that the image path is here. And this is the name of the person, Richard Helfand. So similarly, all the others, like here is Richard Patrick, things like that. So as it turns out, like we have 5,000 samples, and each samples contain 62,500 pixels. So it's probably somewhat around 500, I believe, 250 or something, 250 to 250, something like that. So it is a flattened image. So we have 5,000 different flattened images, and there's a 500 numbers. So now what we're going to do is we are going to stratify field. We are going to remove the classes which contains only one sample. It's not necessary, but we are doing it because the stratify split requires only those classes which have more than one sample. We can just use print test split, that's going to work. That's not a biggie, but for the time being, we're using this shovel split that requires, to perform this step. So after train test splitting, we have 2,747 samples in train and 687 samples in test. And the reason being the number of one classes are huge. So it has removed roughly around 1,500 or so classes. So that's why we have reduced sample space. So now is where the main code is going to work. So now the thing is, see, we have got all the sample images, which is faces, like here. So what are you going to do with that? The thing is, the way algorithm work is, first we need to find out what our mean face is. What even mean face is, we just take an average of all the faces, like 5,000 faces, or in our case 2,747 faces, and just average them up. So there are two ways to do it. We can take an NP-mean, or we can use a PCA, but we haven't done PCA yet, so we are going to skip that. So it turns out this is the average of all the faces. Look like a face, right? Yeah. So now what we are going to do is, we are going to run our PCA on top of that. So now when we have run our PCA, so uh, what happens is we got reduced dimensionality space. So originally our dimension was 62,500 pixels. Now it reduced to 100 pixels. So we have 5,000 by 100 samples now. Originally we have 5,000 by 62,500 samples. So it's just a standard code. We could just run PCA, the number of components we want, and call fit standard SQL syntax, and get our PCA vector. So now the thing with PCA is it retains a n component thing, which means every component, like in our case 100, every component will have a shape like 100 by like 1 by 62,500, and we are going to use this component, which is our eigenvector, to generate eigenfaces. So turns out if we directly take n components from PCA dot components and reshape it into original shape, we get our eigenfaces. This is the representation that our PCA has learned. So we have hundreds of those representations. So each representation look like this. So each representation is some kind of face. And the way our algorithm is going to work is, the original face is going to be converted into 100 different numbers, and each number will say, okay, this face contributes 0.2%, this face contributes 0.3%, and similarly all the faces contribute some of the contribution, and we merge all the faces together, we get our original image back. This is compression, because we no longer need to maintain 62,500 pixels, we just maintain 100 different numbers. That's it. So, and by using, by merging these faces, we reconstruct our original image back. So now what we see is, by using, 100 component or 100 and PCA, we retain 85% of the variance in our original data, which is good. If you reduce the dimensionality from 62,500 to 100, we are still retaining 85% of the variance. And we can do some experiment with that, like I've tried using 5 different values from m and see how much variance we get. So it turns out as explainable, like as we increase the dimension or the degree of freedom, the more variance is captured, with the highest capture in 1,000, and if you increase that amount by more, it will again increase the variance count. So now this is our PCA generation, the simple PCA. Now how we are going to do a reconstruction with that? So remember, right now for each image we have 100 different values. Here we have 150 values, here we have 1,000 values, and we are going to use this value to reconstruct the original image. So how we are going to do is simple. So this is the logic, like ignore everything, is just duplicate. I'm just going to explain one equation, and which is going to sounds perfect. Like, okay, now when we do we run PCA on top of our original image, we are going to get a vector. Okay, and when we are going to run our components, we can cross product them and we'll get our final image back. What I mean by that is our PC100 components of shape, okay, and our images of shape, because each image when transformed by PCA will get converted into 100 different numbers, which is present here. And our fixed value, which is going to remain fixed, is 100 by 6500, which is so learned at train time. So when we take a dot product of that, what we are going to get is 1 by 62,500, which is just an image. We can resize the image to the original, like, square root of this, and square root is, I believe it get 250, something like that, 250, 250 or 256, 256, and we'll get the original image back. Now, the thing is, it sounds well good, but turns out we need to add the mean face which we generated earlier to this component as well to get our final image. And we have done it right now. So this is just a code for that. It's here. So here you can see, right? So there are 10 different images from test data set that we have used, like 3 different images. When we try to reconstruct is using 100 different components, you can see the blurry image. 150 slightly getting better, 200 slightly getting more better, 500 much better. It's a crispier image. In case of 1000, we can see, okay, almost all, rather than sharpness, all the distinct features are being retained, and we can just add the numbers here, like 250 something, a random number like 43, 120, and something like that, and see how it's going to work out. Now, it's not a perfect, but it is kind of generating what we want to generate. So this we have already seen. Now, okay, this is a funny one. See, I believe this is Hillary. No, this is some actress, right? Okay, so you can see that's a funny looking face, funny looking face, funny looking face, slightly generating some of the texture of the face here, features, and here it retains most of the features that were there. And similarly here, like this, I'm not even able to recognize. Here we are not even having the mustache, and here we are getting better and better. It turns out, the more number of components we are going to retain, the more eigen faces we are going to get, and the weighted sum of that is going to be more fruitful or more constructive in that regard, the original reconstruction. So this is eigen faces using PCA, and one of the application is compression and a reconstruction of the image. So we can compress the image really hard, like use a 62,500 dimension to just a few numbers, and then reconstruct that image later on. We can also use this for recognition, say like like certain the idea behind that is these have certain properties, and if we just slide through a image and see the property exists, I use interpret or something like that, and if you're able to find some areas which makes some correlation, we can just say, okay, this might contain faces or something. Just a vague idea, but here's a picture, and we, of course, we can pass it to a classification and assume image or something. So now the technique is cool. Time for drawback. What's the biggest drawback of this technique? The drawback which I found is, see, what it needs is the training time is assuming that we have got all the images in a certain alignment. By alignment, I mean, since the PCA it is assuming that all the columns are same, in which our cases is like 0 0 0 0 pixel, 0 1 pixel, 0 1 pixel. So it means is we have to perfectly align the eyes of all the images to a particular place, nose of images to a particular place. It could be slight variation, but not that much, you know. So as you can see, all the images are center aligned, which is pretty much high quality. So it's a good technique, but not a perfect one. And if you don't want to do, if you want to replicate this experiment, you can just download, the original images, or you can create your own. Of course, you don't have to do the alignment manually. You can just use any automation script to align this. For that, what you need to find is pretty much, I believe, a classifier there. So you can just use a so how to automate generation, like just use a hard cascading classifier to identify the eye region, and then using some OpenCV operation just adjust the pixel and zoom in, zoom out, because it's not going perfect. Yeah, that's it, like data generation process. But you don't have to do that. It's not that much optimal. It's fun way of knowing, that something like this exists. And this technique has been used, probably at multiple other applications like speech, because the idea is still same. You have a vast majority of signal. You can compress it and decompress it. So you're going to lose some information, but not that much.